In this video, we're going to use the sine law and the cosine law to answer word problems. We want to know a few different terms. So one of them is an angle of elevation. When someone looks up at an object, the angle of elevation is the angle made by the person's line of vision with a horizontal line. The horizontal line might be imaginary or it might be real, but the angle of elevation is always with the horizontal and never the vertical. So, for example, if a person looks up at the top of a tall building at an angle of elevation of 20 degrees, the angle of elevation is as shown in the diagram. It's with a horizontal line, not with a vertical line. And an angle of depression occurs when someone looks down at an object. The angle of depression is made by the person's line of vision with a horizontal line. And the horizontal line might be imaginary or it might be real, but the angle of depression will always be with the horizontal and never the vertical. So, for example, if a pilot of an airplane looked down at an airport at an angle of depression of 15 degrees, the angle of depression would look like what you see in front of you there. Okay, there'd be an imaginary horizontal line for you to consider and a 15-degree angle with that imaginary horizontal line. Now, we also talk a lot about bearings. There are two types of bearings. In one type, the question might indicate someone is heading north or southwest or south 15 degrees east or something like that. And in those situations, just remember that on a grid, north, south, east, and west look like what you see on your screen. And now, if someone's traveling southwest or northwest or northeast or southeast, there are 45-degree angles. So, for instance, someone traveling southwest, we would draw a 45-degree angle here and here. And that's true regardless of which one of those four directions you're going. Okay, it's always 45-degree angles in those situations. Now, if someone's traveling north 30 degrees east, that's presented as follows. You go along the north and then you make an angle towards the east of 30 degrees with the north. And also sometimes you'll see a question say that you're heading 15 degrees south of west. So if that happens, you can show it as shown there. 15 degrees south of west means west 15 degrees south. Okay? Now, another way of expressing bearings is sometimes to simply say Fiona looks out at a bearing of 150 degrees. And if a question is worded like that, then it's up to the reader to determine what direction represents 0 degrees and what direction, whether clockwise or counterclockwise, the reader needs to rotate 150 degrees to reach the destination. So the two most common approaches are some people treat north as 0 degrees and rotate clockwise from there. Another situation, which kind of falls more in line with what we do in most questions involving angles, is to treat east as 0 degrees and then rotate counterclockwise from there. That mimics a positive x-axis representing 0 degrees and then rotating through quadrants 1, 2, 3, and 4. Now, it doesn't matter which of those two approaches you use, as long as you're consistent and use the same approach for each bearing stated in your question. Now, I tend to use approach number 1, and I'll do so within this PowerPoint presentation, but if you use approach number 2 or another approach, you get the same answer, provided that your approach is consistent. So let's say Skippy is 500 meters, from the base of a flagpole, and he looks up at the flag at the top of the pole at an angle of elevation of 8 degrees. We want to know the height of the flag. So what we do is we put Skippy at one end here, and we put the flagpole here, and we see that he's 500 meters away, and we want to draw an angle of elevation of 8 degrees. We assume a flagpole is made at a 90-degree angle to the ground, and so we can use SOHCAHTOA if you like, or you can use the sine law. Here we'll use the sine law, but first we're going to note that that third angle in the triangle is going to be 82 degrees. And so putting that in mind, we see that h over the sine of 8 degrees will equal 500 over the sine of 82 degrees. So h will equal 500 sine of 8 degrees over sine of 82 degrees, meaning h will end up equaling roughly 70.3. And we can say the height of the flag is roughly 70.3 meters. Now, suppose New Swan is at the east end of a soccer field and he's looking due west at the top of a building at an angle of elevation of 11 degrees. And suppose Krisha is at the west end of the same field, also looking due west at the top of the same building at an angle of elevation of 25 degrees. We know the building's 35 meters high. We want to know how long the field is. At first glance, it might be a little bit tough for you to consider how does this look when you draw the diagram. Well, here it is. We imagine New Swan is here. He's at the east end. And Krisha is here. She's at the west end of the field, and the field is in green. New Swan is looking up at the building at an angle of elevation of 11 degrees. And Krisha is looking up at the top of the building at an angle of elevation of 25 degrees. And so, if you think about it this way, you realize that you can put a 65-degree angle where it belongs, right there. And because we know that there's a 180 degrees in a triangle. Now, what we can do is we can figure out the value of x. We can say x over the sine of 90 degrees will equal 35 over the sine of 25 degrees. And using that information, we're going to be able to figure out how big x is. X is roughly 82.8. So we can put an 82.8 there. And now we can put a 155-degree angle where it belongs. See, because there's a 25-degree angle here and a 155-degree angle here. And now, believe it or not, we actually know a lot about this triangle that we need to. As soon as you know two angles of a triangle, it's often just natural for you to put the third angle in. So if we have an 11-degree angle and a 155-degree angle both within one triangle, we can put the 14-degree angle where it belongs. Okay? And we can get rid of everything else and just focus on the information at hand and the fact that we want to know how long the field is. Well, this is a perfect sine law opportunity. The field length will be f, and we can say that using the sine law, f over the sine of 14 degrees, because those are opposite, that f and that 14 degrees are opposite, will equal 82.8, which is the side length over the sine of 11. And it's a little tough to see, but those are actually all opposite each other within that triangle. And doing all that information, we see that f is roughly equal to 105.0. And so we can say the field is approximately 105.0 meters long. Now, imagine there's a nice place called Happy Harbor, and Jolene leaves Happy Harbor in her boat at noon and travels northwest at a constant speed of 50 kilometers an hour. Now, Inez also leaves Happy Harbor, and in her boat at 1 o'clock p.m., she travels north 30 degrees east at a constant speed of 40 kilometers an hour. We want to know how far apart they are at 4 o'clock p.m., and we also want to know that if at that moment Inez decides she'd like to visit Jolene, what direction should she head? All right, so some interesting stuff happening here. First, in that diagram that we have of where Jolene and Inez both left, let's add the 45 and 30-degree angle the way you see. I'll show you one more time. Look in the diagram. We'll make that a 75-degree angle. Now, we know Inez has traveled 120 kilometers because she's been traveling 40 kilometers an hour for 3 hours. And we know Jolene's traveled 200 kilometers because she's been traveling 50 kilometers an hour for 4 hours. We want to know how far apart these two people are. So we can simply use the cosine law. D squared equals 200 squared plus 120 squared minus 2 times 200 times 120 times the cos of 75. Ultimately, we see D is roughly equal to 204.9. And we see that these two people are roughly 204.9 kilometers apart. We've now successfully answered part A. Now what we're going to do is something kind of interesting. We want to know, so going back to this, we figured out how long D is. D is 204.9. Now, let's redraw this triangle using all the information we know. We know that Happy Harbor's down here. We know that Inez left at north 30 degrees east. And she got to this point that I'm labeling with a little circle there, right by the eye, with a little dot. Now, at that point right there, let's draw a new north, south, east, west grid. Okay, so we draw that right here. That's going to actually be really important. Whenever you want to know what direction to leave from a certain person or place in a situation like this, we are often going to draw a new north, south, east, west grid right there. Okay? Now, we're going to use the Z pattern as it relates to Inez. See, if there's a 30-degree angle here, then using a Z pattern, there's going to be a 30-degree angle in there as well. Because we know this north is parallel with this north. And so we've created a Z pattern. So we can put a 30-degree angle right there. What that means is now we can put in the relevant side lengths. And we just have to find out the value of theta. And we can do that because, going back a couple of slides again, putting in the relevant side lengths, we now know all of the side lengths of this triangle. And we know the magnitude of that angle being 75 degrees. And it's going to be pretty easy for us to find out how big theta is. Okay, so we can use a cosine law approach here. We can say 200 squared equals 120 squared plus 204.9 squared minus 2 times 120 times 204.9 times the cos of theta. Using that approach, we get that theta equals roughly 70.5 degrees. So that theta there is a 70.5 degree angle. But I want you to keep in mind one thing. Within there, within theta, there's actually a 60-degree angle right here. Because if that's 30 degrees, I know that this little part of theta that I'm shading in red right here, that's got to be 60 degrees. We have a 30-degree angle and a 60-degree angle made. And so now, since that's true, that's the blue one. So to make it a little more clear, we know that this triangle has a 30-degree angle, a 60-degree angle, and a 90-degree angle. I know that that 90-degree angle is 90 because it's an angle between a line that I know is going north and another line that I know is going east-west. So since that I know that's 90 and I know that's 30, I know that this is 60. But I also know that this bigger angle, the one incorporating both the blue and the green part of the angle, I know that that's 70.5. So that means the green part of the angle must be 10.5. But the green part of the angle represents how far north of west Inez is going. That little angle there, that's a 10.5 degree angle. So I'm able to say Inez is going west 10.5 degrees north, or equivalently, I'm able to say north 79.5 degrees west. Now imagine we have Lila in a lighthouse looking out at a bearing of 125 degrees and seeing Michaela 90 meters away. Then Naomi looks out at a bearing of 70 degrees and sees, Lila's in the lighthouse, looks out at a bearing of 125, sees Michaela 90 meters away. Naomi sees Lila at a bearing of 70 degrees, sees Michaela at a bearing of 100 degrees. We want to know how far Naomi is from Lila and how far Naomi is from Michaela. So what we're going to do here, we're going to imagine that there's a lighthouse. I'll back up a couple steps. We're going to imagine there's a lighthouse here. Lila's at it. We're going to let straight up and down be 0 degrees. And we're going to see that when Lila looks out at 125 degrees, she sees Michaela. And when Naomi sees Lila at a bearing of 70 degrees and sees Michaela at a bearing of 100 degrees. So it's going to get a little complicated, but we can handle it. So watch this. There's Lila looking out at 125 degrees at Michaela. So that means she's looking out. There's a 35-degree angle there. So there's a 55-degree angle here. Now we're going to find a spot for Naomi. At first, we'll estimate where she would need to be to see Lila at the bearing of 70 degrees. And we say, okay, maybe she's right there. Because Naomi's looking out at Lila at a bearing of 70 degrees. That means, since we already established early in the question that we would let 0 degrees be straight up and we'd count positive clockwise, we have to do the same for Naomi. So Naomi is down here. She looks out at, um, she, if she rotates from looking straight up about 70 degrees, she sees Lila. So far we have a good spot for Naomi. The hardest part of this question might be finding a good spot for Naomi. And at first, this seems reasonable because it looks like she's looking out at Lila at approximately 70 degrees. But then we want to make sure that the bearing she has for Michaela is roughly 100 degrees. And we actually see in this case that it's not, because that looks more like a 90-degree bearing. Okay. So what we want to do, we want to move Naomi up a little bit. So we put Naomi here. So still, from straight up and down, this looks like a 70-degree angle, sorry, where Naomi can see Lila. And from straight up and down, this looks like about a 100-degree angle where she can see Michaela. Yeah, that looks like about a 100-degree angle. So we've put her in a great spot, and that's probably the toughest part of this question. Okay? So now we are going to use a little bit of common sense. We said a little while ago that Naomi, from straight up and down to seeing Lila, we have a 70-degree angle. Well, that means there's going to be a little 20-degree angle here and a little 10-degree angle here because there's 100 degrees for her to see Michaela. Now, what we're going to do, we're going to make a couple of Z patterns here. We're going to see that if we do that, we can put a little 10-degree angle here for Michaela using a Z pattern. Here's the Z pattern. The east-west line, they're parallel for both, and we have a Z pattern in between. Okay? Alrighty, and so what we're able to do is say that there's about a 125 degree, that there is a 125 degree angle there where it shows in the triangle LMN, and we have a 30-degree angle there. And so since there's a 125-degree angle and a 30-degree angle, there must be a 25-degree angle down there. And so we can eliminate all the unnecessary information and just focus on that triangle. And we add in the known side length that Lila and Michaela are 90 meters apart from each other. And we just do a couple of simple sine laws. So 90 degrees over the sine of 90 meters over the sine of 30 degrees will equal x over the sine of 125 degrees. So x will roughly equal 147.4. And 90 meters over the sine of 30 degrees will equal y over the sine of 25 degrees, meaning y will be roughly 76.1. And we can say, therefore, that Naomi is approximately 76.1 meters from Lila and is approximately 147.4 meters away from Michaela.